So today I shall mostly speak about two-dimensional problems, and by this I mean that yes, today both models I told about, they were one-dimensional just with respect to one variable. It was either an axis or a planar such a rib. But today I shall speak about models in which the domain in which we study the differential operator. So it's infinite with respect to two variables. So it's a two-dimensional in this sense. So the simplest example is, of course, the operator on the plane. So we can think about something like this, xy, and delta is the usual Laplacian. And let's say that V, for instance, is C0 on R2. So it's some potential with a compact support. And again, the question is the same. What can we say about the spectrum of this operator as epsilon is small and positive? Here again, since V has a compact support, then the essential spectrum of such operator can be found very easily. It's the same for all epsilon, including the case epsilon being 0. And this is just a half axis once again. So we again have the same picture. This is the essential spectrum. And again, we can expect that for some potentials, at least for some potentials for small epsilon, we can get an eigenvalue somewhere here. And this is indeed the case. This is true. And we even know how to study the corresponding eigenvalue problem. So they first again say that this lambda is minus k squared. Then we rewrite it. Again, I can even omit this like this. And as a next step, we of course move this spectral part into the left, and this part goes to the right. Then the next step is, of course, to consider the equation for the resolvent or the unperturbed operator, and assume that F has a compact support on R2. Of course, this problem, this equation, can be solved explicitly, and just because it's very simple. And the solution is given in terms of, let me see, in terms of the Hankel function. As far as I remember, so I haven't, it seems that I haven't written it here, but as far as I remember, it's something like this, that u of x. So let me write here just x, and x will be x1, x2. And here I should also have x1, x2. And then here I have u of x, and it will be a convolution with the corresponding fundamental solution, which is of such form, y dy. And the kernel is just something like, as far as I remember, it was 2pi, maybe, no, with 4. And it was a Hankel function. And here it was I, k, absolute value of x minus y, where h0 is a Hankel function. So it's a special function, and so it is a Hankel function of first kind and zero order. And actually, it's not so important how this function looks like, but the point is that, so just two main points is that h0 of I, k, x, y, even with this constant, so it behaves as follows. It says some constant, C0, it doesn't matter how it looks, but by the way, it should be 1 over 2 pi, right? Logarithm of k.
Near 0.
Yes, it's near 0 plus something. Actually, it's okay, but there is also a logarithm, of course, x minus y. There is also some constant. Plus something. And this something actually, if we consider is as a function of this variable, so h0 behaves like O of z squared logarithm z. And this is the behavior when k goes to 0. So for small k, this function behaves like this. And at infinity, it behaves something like exponent, again, something like this, when x minus y goes to infinity. So actually, it means that the solution to this problem given by this, so this is a problem, this is equation, this is a solution. So this solution decays exponentially at infinity when real part of k is positive, then it grows exponentially at infinity when real part is negative, and at 0 it has the following behavior. So it has a logarithmic singularity. And the main point is that when f is of compact support, then we can continue this formula for complex k. So once we say that f is of compact support, this formula actually works for all complex k, and for some k the solution decays exponentially at infinity, and so this is for such k. And for other case, when the real part of k is negative, this solution grows at infinity, and at 0 it behaves as it is written. It means actually that we again consider u of x as the action of some operator a of k on f. And for this a of k, we can say that it behaves something like 1 over 2 pi logarithm k, and here will be a0 acting on f, and then some bounded operator, where A0 of f, I can even skip this one and move it here, will be again something like integral. It's something like this. So this one is bounded. Then actually we can repeat all the calculations I showed. And finally, what shall we get? Finally, so as far as we know already, we shall get an equation for k. And first, what we should do, we should look what we have here. We have here logarithm. So we shall get something like logarithm k equals to minus epsilon f of k epsilon. So yesterday we had here 1 over k. Now we have here logarithm instead. So finally, the only difference will be on this equation. So this function, which we have here, when it goes to the left-hand side, and the rest looks like this. Of course, now this function is not holomorphic in k, and there is also a gentle issue with a branch of this logarithm. But all these issues can be solved, actually. The analysis of such equation can be also done, but it is done not only by the methods of theory of complex variables, but also some means by means from the mathematical analysis. And finally, all this stuff, actually all this is not important, just to see what we can get. So finally, the left-hand side will behave like this. And it means that the root of this equation will be exponentially small. Wait, it will be, no, it's not like this, I made a mistake. So we had here, yesterday we had here 1 over k, and then this k appeared in the left-hand side. So we have here logarithm, which should be rewritten as 1 over logarithm. And then in the left-hand side, we shall get 1 over logarithm, like this. This one should be small. This one is small, and this one should be small. Then finally, if we solve asymptotically this equation, we shall get the following thing. So this logarithm equals to 1 minus epsilon c0 plus O of epsilon squared. And then we see that k behaves like exponent in the power in such power, so exponential in such power. And it means that actually, so and this constant c0 can be found. So we see now that this root of this equation, it is, so if c0 is positive, for instance, then this root is exponentially small. It is not power like in one-dimensional case. Now it is exponentially small, and the explanation of this effect is very simple. This is because we had here not a pole, but logarithm instead. So the logarithmic singularity finally gives rise to exponentially small values of k. And then, of course, we can again get an eigenvalue which behaves something like this: epsilon constant 1 over epsilon, where c is positive. So as we see now, this effect is very sensible to the dimension of a problem, and actually in 2 dimensions it looks like this. However, this is not the only possible case. This is not the only possible situation which can happen in 2-dimensional case. And in order to show what else can happen, actually we can think about such model. We can say take some potential plus epsilon double V. So here we had only, before we had, so when epsilon was 0, for epsilon being 0, it was just a Laplacian. For instance, we can also deal with the case where when epsilon is 0, we have not only the Laplacian, but also some potential. And I shall not speak about this model. I shall rather speak about another model, which is a generalization of this waveguide problem which I discussed yesterday. Now it's 3-dimensional analog, and it's imposed. It's stated as follows. So we have 2 planes, 2 infinite planes in R3, and the distance between these planes is pi. And on one of these planes, we just choose some domain, say it will be omega L. And in this plane, I consider, say, operator of this form, Laplacian plus potential. It's also possible to deal with the magnetic Schrödinger operator. We can also think that we can also study the following case. But actually, this one is enough. And V is of compact support, say even C0 infinity. And the boundary conditions as follows. Here we have Dirichlet, and Neumann. So these are just 2 planes. So finally, this is a 3-dimensional layer of a fixed width. And here we have the first boundary condition, and on the lower part of the boundary we have a Neumann window, so a bounded domain on which the Neumann condition is imposed. And on the rest of this plane we have Dirichlet boundary condition. So what is omega L? Omega L actually is introduced as follows. These are all x, such that x3 is 0, so this is the lower plane. And then we say that these are all points x prime, such that x prime minus x0, I want to scale it, L in the power minus 1 belongs to some fixed domain, where omega is some bounded and compact set from R2. And for simplicity, we just assume that it has infinitely differential boundary. So what we do actually is that we choose some point on this lower plane, then we put a fixed domain on it so that this point is inside this domain, and then
L is small or large?
L is fixed. So when L is some parameter, and when we increase it or make it small, so this Neumann window also is rescaled. And for instance, well, when L is almost 0, then this window is almost a point. When L is large, then the size of this window also is also big. So the linear size of this window is of order L. And then what I do is that I increase L and see what happen, what is going on with my spectrum. And here the general situation is as follows. So it's actually the same as for planar case. Again, when L is 0, then the spectrum of such operator. So, and let this be HL. This is an operator. The situation here is the same. So for L being 0, the spectrum consists of just of its essential component, and this is a half line 1 plus infinity. As soon as L is...
Now you have the magnetic field.
Okay, I should say here that even if I have it here, then I assume that it's also of compact support.
But you speak about the general.
Doesn't matter, actually. I speak about both. I can't. So all these things I have here, so it works for both cases. Actually, we can even have here a more general second-order elliptic operator. I do believe that it is doable, but technically it's much more complicated because you have to care about some local flattening of a boundary change, local change of variables, so just plenty of technicalities. So, and once L is positive, it means that as soon as we have some Neumann window, doesn't matter whether it's big or small, then immediately we have that the point spectrum is non-empty, and the essential spectrum is actually the same. Okay, and this is true. This is true, for instance, when V0A is 0. If we have some general V and A, then probably for small windows this doesn't work. But in general, no matter whether V and A are 0 or not, so in general case, there exist some numbers L1, L2, L3, etc. So that as soon as L is greater than Ln, then the number of eigenvalues, of discrete eigenvalues is exactly n. It means that if we have a Neumann window, when we make it bigger, bigger, and bigger, and at some point we shall get an eigenvalue appearing from the threshold of the essential spectrum. Then we make it bigger, even more bigger, then this eigenvalue goes to the left, and at some point when we pass L2, we shall, so this one will come here, and we shall get one more eigenvalue. It's also possible that at some, like for special shapes of this window and for some special choices of V and A, it's possible that, say, for some critical values of L, we can get not one emergent eigenvalues, but two of them. This is also possible. We can have even more emergent eigenvalues at once. For instance, this is so the simplest case when this is obviously true is if we consider just a Laplacian and our whole is just a circle. So if this is just a circle, then of course it's clear that if there is some eigenvalue which emerges, we can rotate the picture. And if the associated eigenfunction is not radial, which is usually not the case, then of course this emergent eigenvalue will be double. So generally the picture is the same as it was for this one-dimensional model. But actually the phenomenon itself is completely different in the sense that the behavior of these eigenvalues is completely different, and there are several quite different cases. So how to solve this problem? Of course, we should consider, say, operator H0, which is, for instance, with a magnetic potential or just with the potential. And then we consider equation, actually not even like this. So what we should do, we should solve the equation of this form, assuming that L goes through critical shape. So we assume that we have a critical shape, and what is the critical shape means that when L goes through this shape, when we make window larger, then we shall see some additional eigenvalues emerging from the threshold. And yesterday I said that the shape is critical when we have a virtual level at the bottom of the central spectrum. So here we should have some virtual level. So assume that we have this virtual level. Then, of course, what we should do is first we should understand the behavior of the solution to this problem. F, when F is of compact support, let this domain be pi, so C0 pi. And then we ask what can we say about the solution to this problem, how it behaves. Of course, it's in the case when we don't have any window here, so just one plane and the second plane and no window, of course this equation can be solved by separation of variables. We can so we can write an expansion with respect to signs, which are written in terms of x3. And then on the planes, we shall actually have equations of such form. And then each of these equations can be solved by this integral, of course. But if we have window, then again there is a problem how to find this solution. And we even don't need to know its explicit form. We need to know how this solution behaves at infinity and how it behaves for small k. These are the only two things we need. So actually we need something like this. We should have something like this. And also we need to know the behavior at infinity, that's all. Of course, the simplest way here is again to employ this technique by Maida, which I mentioned. So this technique with function v and double v, and then where we construct the solution as interpolation by means of some cutoff function. The only difference that all this stuff now goes in a three-dimensional level, and for v we just remove the window, and for v we don't introduce any boundary conditions. So we just choose for v something. So for v we choose an equation of such form. Actually, this equation comes from the following observation. So if we need to study this equation for sufficiently large x, we don't have potential, we don't have magnetic field, we have just a Laplacian. Here I also should, so here there should be 1 v minus 1 plus k squared. Yes, it should be like this. So for sufficiently large x, we don't have v, we don't have a, and at infinity, this equation looks like this. So this is why, as the function v, we choose such function, and we can find it explicitly via as an infinite series by separation of variables. And all this stuff, all this window, the potential, this A, this V, it actually it is taken into account the function, this second function. And then finally, in the function V, I shall have a logarithmic term just because I had this, just because I had it here. And then this equation with the compact O operator will read as follows. It will be something like this. Actually, there should be here J equals to F. And this T of K will behave something. So it's the form of this T of K will be something like this. It will be T1 of K squared plus T2 of K squared. And both these operators are compact, and they are holomorphic with respect to K squared. Then it is approximately, in my paper, it was approximately 15 pages of studying how the inverse or operator looks like, and what we can finally say about U. And what we can say about U, this is now the most important question. And actually, only now I start explaining what do I mean by the critical shape, and what is the virtual level, which is actually how the associated virtual states can look like so in this two-dimensional case. So the point is as follows. So in 1D case, as far as you remember, it was so that all this resolvent behaved like 1 over K. And here I had some functional. It was f dx with minus 2 as far as I remember. It was in 1D case. And for this strip, similar term was like 1 over K, some constant, phi n, f, phi n, etc., where phi n was a non-zero solution associated with the virtual level, right? And here one, as I said, one was also a solution associated with the virtual level because d over dx2, 1 is 0, 1. So it means that for my problem, in order to understand how the solution to this free resolvent behaves for small k, actually first I should study the same problem with 0f, with 0k. So I should again take the same layer, fix here this window, and the equation will be like this. And I should write here phi equals to 0. And then I should ask myself what kind of solutions I can have. Namely, what is the behavior of these solutions at infinity? Their behavior is the main point here. OK, so I said that A is compactly supported, D is compactly supported. So at infinity, quite far from their support and quite far from this window, the equation will be simplified like this, right? This is as x1, x2 goes to infinity, right? This is how it looks like. So at infinity, I don't have any window, I don't have any A, any V, I have just a Laplacian minus 1. And this equation can be solved by separation of variables. And the first transversal sign will give me something like, say, phi of x prime sine x3, right? Then for this phi, I shall simply get the Laplace equation. because this -1 will be killed by sign. Good. What are possible behavior of harmonic function on the plane at infinity? So if we want to know all possible behaviors, the first case is that phi behaves as logarithm, right? So I don't care about the center. I'm just speaking about how the asymptotics or this harmonic function can look like at infinity.
You take analytic function and real part.
Okay, so actually I don't, from the beginning, I do know that if I speak about virtual level, then the solution should be somehow bounded at infinity, like 1 for the axis or bounded function here. Logarithm actually grows, but not very quickly. This is why, so let's take it into account. So growing solution is logarithm. The next possible case is that phi is constant. This is also possible. This is bounded solution. The next case is that phi behaves as c1x1, c2x2 over x prime squared, which actually means it's a c1r in the power -1 cosine theta plus c2r in the power -1 sine theta, right? So this is the real part of the function that in the power -1 and imaginary part and like this one. And actually then I can have also some solutions which behaves as 1 over modulus of x in some power m, where m is greater or equal than 2. Okay, so the behavior at infinity can be, so it can be a logarithmically growing solution. It can be constant. It can be weakly decaying case. By weakly decaying, I mean that at infinity, this function is not in L2. It decays, but not very quickly. And all this, and the fourth case corresponds to the situation when all these solutions belong to L2 at infinity, and actually it means that so if we have a solution which behaves like this, it's not even the virtual level, it's an eigenfunction. So it means that at the bottom of essential spectrum, we have an embedded eigenvalue. This case, the second case, and the third case corresponds to the real virtual level. So we have something at the bottom, and this something is not an eigenvalue. This is exactly virtual level. Then the next question, which of this solution will emerge, will appear in this function u? The answer is that as soon as that it's for almost all L, we always have solution which behaves like this. This is a general case. If we put any window of any shape, we almost always have solution which behaves like this. And if this is the case, then all other solutions are not possible. So actually this one is not possible, but these two are possible. So for instance, if we have only such solution and we don't have the case 2, 3, 4, then this is not a virtual level in the sense that this function does not appear in U, and when we make window larger, there is nothing. There are no emergent eigenvalues. So this is a general case. So this is not a sign of having a virtual level. So we shouldn't care about this solution. What we should really care about is about the shapes when we have either such function or such or such. So let me write here, I shall write here phi2 I shall write here phi3, here phi4. And it turns out that in case 2, and it's also possible that we can have, for instance, one solution of such form, up to 2 solutions of such form, and finitely many eigenfunctions. We cannot have infinitely many eigenfunctions. This was proven. So if we have an embedded eigenvalue, it's of a finite multiplicity. We can have any combinations of these solutions, and each of these solutions makes its own contribution to the function u. So in case 2, u behaves like this. It's a logarithm k with some constant, say c2, and we have here this. So it's not actually this phi to generate such phi. So we shall have here phi2 and the scalar product, not the scalar product, but actually the integral f2 dx. This is the term which appears due to the presence of such solution. So if we have a solution which is constant at infinity, it behaves as a constant, it generates a logarithmic term in the resolvent of the unperturbed operator. In the case 3, let it be big C in order. So this one is big, these are too small. So here I shall have some constant, and here I shall, let me even copy it properly. It's like this. Minus pi2 pi squared over 2 logarithm k plus some constant. It's like this, and then phi3 dx. And in the case 4, u behaves as some constant, c4, here just k squared, and k squared, and that's all. Here will be phi4 f phi4 integral. It's like this. So they see, depending on how the associated non-zero solutions are associated with the bottom, with the virtual level at the bottom behave at infinity, they generate various terms in the meromorphic continuation of the unperturbed resolvent. If the solution is bounded and at infinity, it produces logarithm. If it is weakly decaying, then it's k squared times logarithm. And if it decays quite fast, so that it's inside L2, if we are in the case of having an embedded eigenvalue, then it's just 1 over k squared. Good. Imagine that we are in case 2, just in case 2, and we don't have any.
Just a question. And to get this, you have to get some information about the resolving, right?
Yes, exactly. So all this information comes from the analysis of this equation. So in paper, it took approximately half, and the total size was something like 35 pages. So it may be like 15 pages of fighting with huge matrices. Since I studied a general case when I have one this, one or two such, and finitely many such solutions, so it was quite complicated. But actually, the main point was again to apply a variation of this Biermann-Schwinger principle to this equation. So just study the behavior with logarithm. And okay, so actually such equations with complete operators, when the operator itself is not holomorphic but have some special behavior at 0, there is also one more variation of the Biermann-Schwinger principle, which I don't know, maybe someone did it before, but actually I understand.
An operator like a Biermann-Schwinger principle, right?
Yeah, so actually what something like this does, yes, something like this, just select from this O operator its bad part and inverse the rest and see what happens. So finally I got such nice formulas, and just imagine that now, so now the next step is to understand what will be the behavior or the eigenvalues.